Okay, so I'd like to do another video here to help you with your project. So let's go here to Blackboard here um, and go to Computer Engineering 1. Um, that's your lab groups here. Did I not put the project up here? Well, let me pause it and grab. Okay, so the screen just flashed here suddenly, but I found where the project was. I will upload this document here. So remember, there are three things here. I'm going to just pause the actual video playback here. Um, the project that's due at the end of the semester, you're going to need a detailed lab report, a power presentation with notes, and then what we call a gate level design. And so we're going to, and with that, we're also going to need simulations. And then we need to design a 4-bit arithmetic and logic unit according to the following specifications here. And what I want you to focus on primarily is getting the A and B such that when you get the outputs, that the sums are getting correctly and that the carryout is correct as well. And then the other function that we want to have here implemented is the subtraction and the increment and decrement done correctly as well. We want to try and get all of these, but the first thing I would shoot for is getting the addition to work correctly. And so I'm going to post a couple videos as the weeks go on here, and I'm also going to have you submit some updated status reports of where you are and where your possible circuit designs are, and award points for those so that we don't fall to the, oh my gosh, it's the first week of May and I haven't done anything regarding this ALU. My project team, we're scrambling and we're not going to get anything done and we're going to do poorly in the course. Because we're not able to do the labs anymore, we want to make this project as robust as possible and learn as much as possible. So this again is the project that we are doing. What I want to show you today is how we can, because we're supposed to do a gate level design, but I want to show us how we can do a gate level design without having this just massive thing of gates. And we're going to use something called hierarchical blocks, and this is in Capture. So if I go to Capture here, CIS or OrCAD Capture, I'm just going to start a new project, and I'm going to call this one here example 1-bit full adder. And we're actually going to create this, and we're going to try and do minimal gates here, and we're going to create this using half adders. And how are we going to do this here? Well, first off, let me just close this out here and get back to here. So first off, one thing that might become useful here is, where is it here? The print setup? No, that's not it. Just one second. Okay, I found where it is I want to show you. If you go to options here and schematic page properties, you can actually make this much bigger if your circuit isn't going to fit on one page. So like for instance, I can go to page E here and I'm going to zoom out now, and you can see how small the little label is here now, because that's really the same size as it was before, but this is now our giant piece of paper here. And just to give you an example, if I were to place a component on there, look how small that is, you know. So I mean, that's a huge page, and you can try and draw a circuit like that, but that is going to create issues as far as being able to see what's going on. So I'm going to show you a way going back to just our normal size, is creating something called hierarchical blocks to do our simulations. So first off, I'm going to expand this area and scan the schematic, and I'm going to rename this, and I'm going to call this a 1-bit adder. And what I'm going to do now is I'm actually going to create a new schematic, and I'm going to call this schematic a half adder. Now what's important here is you see this little thing here, this little line here, that means it's something that's called the root. Like I can make the half adder the root, but I don't want it to. We want wherever you're going to build your final circuit, that's what you want to be the root. So I'm going to make, because this is where I'm going to build my final circuit, I'm going to make the 1-bit adder my root. Then if I go into half adder here, I'm going to right click and do a new page, and then I'm just going to call this half adder. And then what I'm going to do is I'm going to draw the circuit for a half adder in here. Now I have been playing around here with some of these libraries for the TTL logic, and some of them don't have their digital simulating properly. I found that the 74HC library is really the one we want to use. So 74HC, and again, if you just go to add your libraries, there will be one here for 74HC, and to find that again, you can pause the video, C, Cadence, SPB 17.2, Tools, Capture, Library, PSpice. It should just default open there, but sometimes it doesn't. So if it doesn't, now you have the path name. All right, so my half adder is a pretty simple circuit. I need an AND gate, so that's 7408. So a 74HC08. I need an AND gate, and then I need an XOR gate. So I don't remember the part number for that, so I'm going to kind of just keep scrolling down through the parts until I see the XOR gate here. Okay, there we go. No, that's an XNOR, never mind. Maybe I scrolled down too far. Oh, there we go. 386. 74HC386. That's my XOR gate. Whoops, I don't need two of them, I just need one. And I did research and found a circuit that basically says if I put this here and this, tie these together, I'm going to just put a wire out here and a wire out here, they're not connected, and then I'm going to put a wire out here and a wire out here, and then I'm going to add some text here just to explain here what we've got. So we've got A, so this would be A, and this is B, and then this is the sum, and then this is my carry. So those aren't net aliases, that's just random text, not random, but that's just text, so it does nothing as far as simulation goes. Now the other thing that you might be able to simulate without this here, but it's often good just to put a ground in there of some sort, because sometimes, even though it's not connected to anything, sometimes PSpice won't run if there's no ground present. Even if it's not connected to anything, it needs a ground. So even though it's digital logic here, and we're not actually using power and ground, it's a good idea to put a ground in there just to be safe. Okay, so that's my half adder. Now, there's a way that you can cascade two half adders to make a full adder. Because basically a full adder, let's just go look here, a full adder block diagram has got A and B and a carry in. and then a sum and a carry out. So the only thing that's different between a half adder and a full adder is a half adder only has A and B and then sum and carry. We don't have the ability to do a carry in on a half adder. But we will need to be able to do that carry in, because what you'll be able to do is then cascade full adders, and you can kind of see some block diagrams already here. Binary adder and subtractor here, and it's a block diagram, half adder and then some full adders. So you see, this is how these hierarchical blocks are going to help us. So instead of having to redraw all these gates all the time, we're just going to make one gate and say, okay, this is how you build a half adder. And then I'm going to have a block for a half adder. And what we need to do in order to do that, you guys would be laughing right now because I'm waving my hands all over the place, is we need to place ports here. Now, you can use any of these ports. It does not matter which one you use. I have favorites that I like to use. I like to use port left L, and I like to use that for the ones that are on the outputs. And then I also like to use the port here, which place ports right here. I also like to do the place port right and the R here. And then this I'm just going to call A again, because that's what I want to give it a name here, because even though I have the text there, I want to label these ports as far as what they actually are. And you'll see why in a second. So I'm going to label those ports A and B. I'm going to label this port sum. I'm going to label this port carry. I'm going to go ahead and save. Now I'm going to go to my 1-bit adder here. And again, just by looking at doing some online research here, full adder from half adder, we look at a block diagram here, and of course you'd want to make sure to find academic resources. I just did this randomly, but you'd want to find a place where it's not just like this random, like lprocus.com kind of thing. You wouldn't want to use Chegg. Chegg I'm not a big fan of, in my opinion. The reason is because it's a bunch of people just posting solutions without necessarily having good explanations. But you might say, okay, well, for instance, this Wikibooks here, okay, it's a wiki, so that's not good. But if you go there, what you can find at the bottom sometimes, and this one does not have it here, but what you can sometimes find is references at the bottom for where you could find to get this information. Okay. So what I want to point out here is that we have these two half adders that are getting cascaded together, and then we have an OR gate that ORs the two carryouts together. So what I want to do is I want to first do place under here, and under place there's a hierarchical block, and there's also one over here on the menu. Right above the port, there's also a place hierarchical block. And so you now need to give it a reference. You need to call it something. So the hierarchical block I'm going to place, I'm going to call it half adder. And then you have to give it an implementation type. Schematic view, VHDL, all sorts of different things. Verilog, all sorts of different VHDL. These are different ways of inputting information into it. Some of you might be familiar with Verilog. That's something computer engineers will talk about in future courses. But we're going to do schematic view because we made a schematic for it. And then the implementation name, well, we only have one schematic that we have created, and so it's the only option is the half adder schematic. And so I'm going to click OK, and then it gives me this little cross here where I can draw, hold my mouse button in and draw and build a block. And so there's my block here. So now one thing you can do here is you can actually move, I'm just moving these, you can move these little connectors here up and down. But basically what this is doing is this is now a box representing this circuit here. And I could make this big or small. I could have made it smaller if I wanted to, and I think you can actually, you can shrink it down a little bit like I did there. So I can make this half adder You know, if I compare it to the size of the circuit, I can make it much smaller. But then it's a hierarchical block, so I know if, like, for instance, I was grading this, I was like, okay, well, you got a hierarchical block of a half adder. Okay, well, now I need to go into the half adder circuit. Okay, yeah, that's drawn correctly, so we're good. Now I just need to see, did you cascade it correctly? Well, I'm going to select this and paste another one in here. Just do a copy and paste. And now notice it gives it a half adder 1 here, because this half adder means it's still, the bottom half adder means it's still referencing this circuit diagram. The top is kind of just the name of the block. So this is half adder, this is half adder 1. If I did another one, for instance, it would be half adder 2, half adder 3, so on and so on. Okay, so now I just need to connect these up correctly. And so if I connect the sum up here to B, put some wires here, and then go here and find an OR gate, because we needed an OR gate. Did I somehow miss the OR gate? That's a NOR gate. That's another NOR, that's exclusive NOR. There we go, that's an OR gate. 74HC2. 74HC32. Okay, so there's my OR gate. And then I put the 2 carries into this. And then we could go ahead and test this 1-bit adder, and that's what I would do, is I would test to see, does this 1-bit adder work at this point? Now, I'm not going to do that. The previous video here shows you how you could test it, but I'm going to go one step further here on how to help you build these adders here. Well, then let's go back here and say, okay, schematic 1-bit adder. Let's go ahead and actually do a new schematic and say, let's do here and have this be a 2-bit adder. And I'm going to put a new page in here and call it 2-bit adder. And what I'm going to do is I'm going to actually make that the root now. And instead of calling this schematic 1, I'm going to call this, rename this as 1-bit adder. Okay. And I should also make sure I put ground in here as well for all of these. Now, why am I doing this here like this? Well, I'm trying to show you how you can, again, use these hierarchical blocks here. Well, now what I have here is I would go ahead and put ports in again. And the ports, I'll put in these ports. And this is CN for carry in. And it would make sense to call these still A and B. And then I need 2 more ports. And this would be my sum. and this would be C out. Now to build a 2-bit adder, there's a couple ways you could do it. The way I would do it here is build a hierarchical block here. So we're going to call this, I'll call it 1-bit adder 0. And schematic view. Now if I look at implementation, there are 2 options here now. I'm going to do the 1-bit adder, draw my little box, and so I've got my A, B, C in, sum and C out here. I'm going to copy that and paste it. 1-bit adder 1 now, so it increments it there. And you can think about it as being the data bit 0. So data bit 0 here, these would be my inputs for data bit 0. Now what you want to tie C into, because we need to tie it to something, is you can do ground, but there are there's digital low here under source. So I can put a digital low there so that that is now grounded. You could also put a half adder here instead of a full adder because we don't need any carry in. So the other option is we could have put a half adder here. But then the sum is going to be, this would be, here I'll put text here. Answer or bit 0 of answer. That's what the sum would be. And then the carry out would go into the carry in of the next one. And then what we would have here, I'll label some text again here. Bit 1 of answer would be there. This would be A0. This would be A1. This would be B0. And this would be B1. And then this carry out I won't label, but that would be an overflow essentially. Like if you're adding 1, 1 and 1, 1 together, for instance, you would wind up with an overflow on that. And so that would give you a carry out there. But then if you were wanting to do a 4-bit adder, well, we can see what would I have to do, because that's what you have to do. We'd have to cascade 4 of these stages. Now, the next question becomes, then how do we test all of these things? Because trying to create digital stimuli, like we did in the first video for every single one of these inputs, that's going to be pretty challenging because you've got really 16 times 16 possibilities. Because you got 4 bits, so there are 16 choices for variable A, there are 16 choices for variable B, and then they can both be different, so you have 16 times 16, which, that does not sound like fun to do. So we're going to use buses to try and simulate this better. And so that's the next thing I'm going to show you here. What I'm going to do here is I'm going to go ahead and continue on in another video in an upcoming week here, showing how we can then use buses to make the simulation of the circuit and seeing if it's adding correctly much easier for us to see. Because instead of having to constantly be looking at like, oh, 0, is that a high or low, we'll be able to look at something, for instance, like, okay, you know, the input was, you know, 3 and the other input was 4, the output should be 7. And we'll be able to look at it something like that using buses. But again, that's what we'll do in a later video. So this should help you start moving forward. So you should be able to get the adder at this point created and start getting it simulated for your labs. And again, remembering you're going to eventually have to create a PowerPoint presentation and everything, but I want to again emphasize these hierarchical blocks, because the reality is if I were to try and draw all of these components in one diagram, especially even just for the 4-bit adder part, it's going to be a pretty complicated circuit diagram. And now here, what we've done instead is we're saying, okay, well, I've got my half adder here, it's 2 components. Then I've got 2 of those, so really there's 4 components going on here, plus a 5th one for the OR gate, so that's 5 components. And then for the 2-bit adder, well, actually, there'd be 10 circuit elements here if we were to draw it all up by hand. So that's the advantage of hierarchical blocks, is that they can actually simplify your diagram significantly. All right, so that's what we'll be working on.